Sometimes large language models just make things up. But what if I told you there's a way to reduce hallucination and improve accuracy? That approach is called Monte Carlo Tree Search, and it provides a way to programmatically get the best answers to a given question using an LLM. In some cases, it can even take the performance and accuracy of a small model like Llama 3 8B up as far as GPT-4 Turbo and a little bit beyond. In this video, I'm going to go through the basics of how Monte Carlo Tree Search works without any advanced maths. Then I'll walk you step by step through a Jupyter notebook that solves some maths problems. Before I explain how the Monte Carlo technique works and go through a Jupyter example, let me show some of the results from a recent paper here that is linked in the slides. It's called Accessing GPT-4 Level Mathematical Olympiad Solutions via Monte Carlo Tree Self-Refine. And the authors here use a Llama 3 8B model, so quite a small model compared to GPT-4. And you can go through the paper, but I've summarized the results here for a high school grade school exams and also for the Math Odyssey test. And what I'm showing is the Llama 3 results, just running a basic chain of thought type prompt, and then Llama 3 8B, where they use this Monte Carlo technique. And for comparison then, we have the GPT-4 Turbo answers right here. Now you can see already that on this grade school exam, the performance goes from 74 up to about 97, and it's only slightly short of GPT-4 Turbo in this case. Now in Math Odyssey, the performance goes way up from about 17% to 49% and actually very slightly exceeds the performance of GPT-4 Turbo. So how is it that using the exact same model and Monte Carlo, we're able to get really significantly better results? To help answer that, I'm going to talk about how answer quality with language models is extremely sensitive to the prompt. And you'll know this already, even if you're new to language models. By making small changes to prompts, you can get different answers and answers of different quality. And this is the core of why Monte Carlo Tree Search works. It's a programmatic way to vary the prompts and refine the answers. That's in essence what Monte Carlo is. Rather than just manually trying to improve the prompts, it will do this in a progressive and programmatic way. So I'll explain how that search method works. And I'll explain it using a very simple example, the question, what is 2 plus 2 plus 2? And we'll see how the tree search addresses that question. Then I'll elaborate a little bit more on the technical detail. I won't get into any too complicated maths, but I do want to show a very basic equation that will explain how Monte Carlo explores new solutions, as well as honing in on the strong solutions that it has, the strong candidates. Then, last of all, I'll go through a notebook demo using Monte Carlo to solve some maths problems before talking about some of the limitations of this approach in terms of cost and then also in terms of the capabilities and types of tests it will do well on or not. So I'm here in OpenAI Chat Playground, and this will allow me to experiment with a variety of models. I'm going to test out GPT-4.0, and I'll set the temperature to 0 just so that we don't have any randomness of sampling affecting our experiment. Now, the question I'm going to ask is, name the town that is both in County Laois and Dublin. So let's just run this question. These are two towns in Ireland. And as you can see, the answer is correct. There's no town that's in both Laois or Dublin because they're separate counties and well, they're not just separate, but they're actually not beside each other. So there's no way for there to be a town straddling both. However, if I modify that prompt and I just put in here, just give the town name, and I run this, it gives the name Portarlington, which is a county, I think in County Laois, but it certainly can't straddle Dublin because the two counties are not beside each other. And the experiment here I'm showing you is illustrating how changes to the prompt affect the quality of the answer that we get here. And this is said differently why you would consider optimizing your prompt when you're trying to get good answers from a language model. And of course, you can do that manually when you're inspecting the results. But what Monte Carlo offers is a programmatic way to basically create some seeds, some seed prompts, iterate on those prompts, then dive deeper on the ones that are good, while also exploring some new options. That's what Monte Carlo does. And it's a lot more efficient than just trying to ad hoc find the best possible prompt and the best possible answer. So let's head back to the presentation and ask the question of, okay, how do we find the best answer, or how do we get a language model to give us its best answer? We know it can give some wrong answers sometimes, it can give some unclear answers, but how do we get the best answer? And the answer is Monte Carlo, which is, as I said already, I'll repeat it again, Monte Carlo is an iterative approach to search for the answer through prompting. Okay, so let's start off with an example, as promised. What is 2 plus 2 plus 2? And typically what we'll do at Monte Carlo is we'll start off with some seed answer, which is usually generic. We don't want to bias the final answer in any particular way. So we'll start off with an answer like, I don't know. And from there, we're going to get the process, and I'll talk about how this works later, but we'll get the process to generate some improved answers. For example, here, the candidate improved answers might be 4 plus 2, and here we have 5. So we've 2 candidate answers. Now, given these candidate answers, we're going to score one of the answers. In this case, we're going to choose to score this one here, 4 plus 2, and we're going to score it between 0 and 100% as 50%. We're going to say this is a 50% score. As you can see, it's not quite the answer which we want, 6, but it's also kind of on the way because it's 4 plus 2. So we score an answer. And then next, what we'll do is move to another iteration. And to do that, we're going to follow the tree through the path of the highest reward. So what we'll do is start at the root of the tree here with I don't know. And we're going to follow down the tree according to the branch that has the highest reward. Here, 50%. And we're going to create 2 more possible candidate answers. And the 2 candidate answers here are 6 and 6 plus 0. So follow the highest node score and then generate new answers. Now, when we've done that, we're going to continue that same process for multiple iterations. There might be a set maximum number of iterations, or until we reach a certain reward. For example, we might decide that if we ever see a reward of 95% or 100%, we'll just stop the process there. So you can see this is very loose, but it gives you an idea of how we recursively generate new answers. Now, something I haven't explained is I haven't explained how we balance digging in on good answers versus exploring new answers. What I've chosen to do in this example is I've just followed the best route, and so I'm continuously expanding the highest reward answer. But what you really want to do is not just expand what you think is the best answer so far, but you want to give a chance to some new seeds or new answers. So as I've written here, the aim is to keep expanding the best answers, but also we want to explore some other answers. And this is called exploitation versus exploration. Exploitation is where you improve on good answers, and exploration is where you expand on nodes that have not yet been addressed. Okay, so the way that we look at exploitation versus exploration is using UCT. UCT is upper confidence bound, and what it provides for is a function that can guide us on which node to choose next. And this function combines 2 things. First of all, there's a term for exploitation, which is really just the average score that the node receives. And when I say node, I really mean answer. So if you have a candidate answer and that node has got an average of, say, 90% as a score, that's going to increase the UCT and make it more likely that we should follow that node versus another node that's scoring something like 20%. So that's exploitation, and it gets us to follow the nodes or answers that are the good ones. Now, on the right-hand side here, we have an exploration term, which encourages us to try out nodes that have not been tested out yet. And the way it does that is by looking at the number of visits to the parent node versus the number of visits to the node. And you can see the number of visits to the node, or the answer, is on the bottom. So, for example, if over here we have not visited the node any times at all, then that means this is going to be a small number of visits. It'll be 0 actually, which would make this value here effectively infinite. And so it would have a very high exploration score, and we would be favoring visiting that node which is unexplored, even versus an explored node that has a high reward score, say of 90%. And as we continue to visit this node here, this one here, more and more and more, what that will do is drive down our desire to explore that node even further, because this exploration value will be reducing. So this is what UCT does. It balances between exploring new nodes versus digging deeper on the nodes that we know are very good. So I'm going to take this framework now and apply it to some toy problems and then to some maths problems in a Jupyter notebook. Now I'm here in the Jupyter notebook where we'll be working on Monte Carlo. And I should note that those of you who have purchased access to lifetime access to the advanced inference repo on GitHub, you can now access the scripts underneath the Monte Carlo folder there. Those of you who don't have access, you can purchase so on trellis.com, or you can even purchase the individual script if you want the cheapest option. So let me go through the high level steps here before I go into the script in a bit more detail. Here's the approach. We're going to start with a seed answer, something like I don't know. Then we'll ask the language model to suggest improvements to that seed answer. Now these are improvements, they're not actually an improved answer. For example, the improvements could be, well, you just said, I don't know, that wasn't an answer, so please give me a clear answer to the question. Step 3, we'll use the suggestions from step 2 to provide 3 improved responses. So these will be new nodes on the graph, and we're going to have 3 responses by querying the language model 3 times with temperature equals 1. And that temperature equals 1 will give variance in those 3 answers in the 3 nodes. By the way, I'm going to use Llama 3 8B, so pretty small model here. In step 4, I'm going to randomly select one of the responses and use the language model to rate that response out of 100. Now that I've rated the response, I'll be able to calculate the UCT, that's the bound for the tree, based on the reward or the rating for the node, if there is a rating, and then based on the number of visits that each node has already had. Just a reminder, UCT is this equation right here. So every node in the graph will now have scores. And next what I do is traverse the tree following the nodes with the highest UCT. So I go through from the root node to the outer nodes based on the nodes that have the highest UCT. And then I repeat the process. So I'll create new nodes via suggestion, improvement, rating, and I'll go back through these steps again and keep on expanding the tree step by step by step. And because I'm using UCT, if I follow the equation here, the way that I traverse the graph is going to depend on some nice balance of exploring and exploiting. So we do need an endpoint. We're going to be querying an LLM, and there are a few options here that are supported by this script. You can use OpenAI. If you like, you can run an OpenAI compatible endpoint using a service like RunPod. I've got some one-click templates here. Or you can use Grok, which is what I'm going to use because it's really fast. You can also use any other OpenAI compatible endpoint. For example, if you're running locally on a laptop, you can set up Llama CPP and you can run /server to run a server. So I'm just going to upgrade pip, install OpenAI. By the way, we are using the OpenAI library no matter what the underlying endpoint is, so you do need to install this no matter what. Next up, I'm going to just get in the model name and the endpoint as well as the API key. So I'm using Grok, so I've put in a model name of Llama 3 8B 81892, which is some specific version that they've launched. And this is the endpoint that I use, an OpenAI style endpoint from Grok. So right here, that's all done. The endpoint is set, the OpenAI base is set, and the API key is set. I've increased my screen size a little bit, and I've now set up a chat completion request. This is just a simple way for me to get a generic response from the API. And I can run a test here just asking to return an array of strings where each string is a season. So you can see if I run that cell. And let's see if it's running. Yeah, we get back a response that is an array of those seasons. So this is the way that I'm going to call the API by calling this function chat completion request. Now I'm going to follow the steps I described earlier. So first I'm going to set up some seed answers. I've got 3 here. I'm just going to pick one randomly as the root seed. There's just one of these that's going to be used. So I really could just use one if I wanted, but I've got a few options here. Next, I'm going to set up my answer improvement and rating pipeline, which requires having a critique step. So I want to get suggestions for improvement, an improvement step, generating actual improved answers, and then a rating step, because we need a rating for calculating UCT, UCT. So here's my function to get a critique, and it inputs the question and the draft answer, which will start off just being the seed answer, and says, please critique the draft answer. Do a careful assessment of whether the answer is correct or not. Consider multiple ways of verifying the correctness. Point out every flaw and hold the draft answer to a high standard. Provide specific recommendations. Think step by step. And do not provide a revised answer. So we don't want the suggestions to have a revised answer. We just want them to be suggestions for improvement. So for example here, with a question of what's the capital of France and a draft answer if the capital of France is Lyon, which is obviously wrong, we can run that and we get initial impression. The answer seems correct, but it's not the capital. Verification, logical fallacy, and then the draft answer is correct. And you can see here, actually, this is just truncated because I've limited the max number of tokens in the response. But this gives you a sense of how a critique can be generated. Next, we're going to improve the answer. So here we input the question, the draft answer, and the critique, which is going to be used to improve the answer. And then we'll say, please improve the draft answer following this format. So we want a reasoning process, verification, and then a final answer. So here we go. This time I've put in the same question and draft answer along with the critique. And the critique here is, that's just wrong. I made that up. And let's run that. And very fast because we're using Grok. The capital of France is Paris. So, I mean, this question is easy, but you can see the critique probably wasn't needed in this case, but you can see just an illustration of how this works. Now, the last step is rating the answer. So we'll say, as an expert on this topic, please provide a detailed critique of the answer, pointing out every flaw. Provide only a critique, not a suggested answer. Rate the answer on a scale of 0 to 100, and we want it to be in this format. So we want a detailed critique and then a rating, because we're then going to do a reject search to just grab this rating here. So that's exactly what I'm doing here. A reject search just to grab the text or the numbers that are after rating, because we're going to need that to input into the UTS calculation. So you'll notice here that I actually do limit the rating so that it's never more than 95. This is something that appears in the paper, and I've used the trick here. I haven't verified that it completely fails if I don't do this, but I just decided to make use of this heuristic. Also, I should point out that I'm not following exactly what the paper is doing. There are different tricks and techniques, but I'm kind of generally following the gist of applying a Monte Carlo approach to language model answer generation. Okay, so let's do a test on this. What is the capital of France? Capital of France is Paris. And we're going to run that. And you can see here we have a reward or a rating of 0.19. So that's actually quite low. And the reason for that, if we print out the critique, we can probably just print out the critique here somehow. Let's see if I print the rating response. So here you can see that although the answer is correct, there's no supporting evidence or explanation. And for that reason, it's providing it with a lower score. So you can see that it is important how you define the rating mechanism for the answer. And this is something that you might have to play around with based on your application. Now, I'm going to be using some maths problems. So there will always be an explanation. So I don't expect to run into this issue. I won't be simply providing a very brief answer like this here. Moving on, I'm going to just set up one more function to get an answer directly from the language model. And this is my baseline comparison, where I'm just querying the language model to solve the problem by itself with no help from Monte Carlo. In this, I use pretty much the same prompting technique as in the improvement function. Please provide the answer with detailed reasoning. Follow this format with reasoning, process, verification, and final answer. So I'm basically using my best type of prompting, so it's somewhat comparable between the baseline and the Monte Carlo approach. And so that function should be set up now. And we're at a point now where we're ready to combine all of these steps into our Monte Carlo search approach. So I'm installing NumPy here and importing it. And now I'm going to go through the setting up of the Monte Carlo approach. which is actually not as bad to follow as you might think it initially is. Notice how up here I'm defining the maximum number of children. Currently it's set to 3. And what this means is that anytime I reach a terminal node and I'm going to generate some new improved answers, I'm going to generate 3 answers. If you want to kind of widen your search or widen the variance at each node, you can increase this to a higher value. Of course, that means that you're going to search more broadly. So it's going to take you more time in order to do that Monte Carlo search. So just for a balance of kind of getting some variance at each node point, but also not taking too long, I've selected a value of 3. So next we'll take a look at the node structure. So every node, which you can think of as an answer, is going to have an associated question. Let me just, I had to take a break in recording because I lost my voice yesterday. So we're back, larger screen size. Every node has a question, an answer, a parent, which is, well, the root node won't have a parent, but other nodes will. Children, of which there are none when we start because we just start with a root node, but there'll be children added over time. Then number of visits. So how many times is that node visited, which means how many times do we actually consider one of its children? That counts as a visit because we will back propagate the reward to all of the parent nodes of that child. And then self.value is the accumulated rewards. So every time there's a child node that we evaluate, we're going to pass that reward back to all of the parent nodes and add it on, accumulate that reward. Next, we have a small function to check if a node is fully expanded. This means, have we created the maximum number of children, which is 3. And once that it has been fully expanded, we're not going to create any more children. Now, to be clear, when I say children, I mean children, not grandchildren, because we will expand those children into further nodes. Next, we have a function to decide the best child. This is only used it's used to determine what path we would want to follow. So we always want to follow the best child path. And you can see here that this is how we implement the formula, where we weigh the exploitation term, which is the value over visits, which is really the average value. And we also weigh the exploration term, which will be very large if a node hasn't been visited and encourage us to visit it. Then we have a simple function here called most visited child. This just returns for a given node what its most visited child is. Now that's different to the best child. The most visited child is counting the number of visits, whereas the best child is counting the largest value of the weight, or what we've called the ECT score. So the reason for this most visited child function is because once we finish running all of the tests, we want to count which child has been visited the most, because that is most likely to be the best answer that we have. Then we have a short function to add a child. So when we're expanding a given node, this function will allow us to append children onto that node. Next, we have a class here to run the Monte Carlo tree simulation. And to run a simulation, we're first going to define a question, define some seed answers from which we'll just pick one of them, define the number of iterations. So that's how many times we'll go through the full process of generating children, evaluating one of them, and propagating back the reward. And also there's going to be a route. So we have one node when we start off the Monte Carlo tree simulation. And that root node is going to be chosen by randomly picking a seed answer from our list of seed answers. Let me take you through now the search function. A few things happen here. First thing is we're selecting a node to expand. The second thing is we expand the node. The third thing is we simulate one of the expanded children. And then with that reward, we back propagate it and accumulate it on all of the parent nodes of that child. So let's go through each of these functions. The first is, how do we select the node to expand? Well, we use this function here. What this function does is it checks that for every fully expanded node, it's going to move to its best child. So using the UTC function, or rather the UCT function, we're going to move along the tree, along the path of the highest UCT by choosing the best child at every point. Once we have the best child, we're going to expand. first of all, we're going to expand into 3 children. That's why it says for j in range max children minus the length of the current children. So this will start off at being 3 minus 0, which will just be 3. So we're going to repeat this process 3 times for 3 children. And for every child, we're going to set the answer of that child equal to the answer and the question of the parent. So we just start off by taking a node and making 3 copies of that. Then for each of the children, we get a critique of the answer. And we take that critique and we input it to get an improved answer. So now each child has got an improved answer. So that's here. We set the child's answer to the improved answer. And then we return at random one of the 3 children. So we return at random one of the 3 children. And that is going to be set here. So that the child that is being returned is being set as node. And then we simulate that node, which means we calculate the reward by sending it to the LLM. So here we simulate by getting the LLM to rate that answer. So to recap, we have a parent, we create 3 children that are copies, we evaluate by critiquing and improving each of the answers. We take one of those random children and we get a rating. And now that we have a rating, we propagate that rating all the way back up the tree in order to update the UCT scores. And that's this function here, self.backpropagate, where you can see we backpropagate the node and the reward, and we're going to pass through the number of visits. So every parent, the visits will be incremented by 1, and every node, the value will be incremented by the reward. And you can see here, this is what's backpropagating because we're setting the node on every iteration to the node of the parent. So that's how we're moving back up to the root node. And that wraps up the search process. And what we can now do is we can set a question and we can run the Monte Carlo Tree Search on that question with our seed answers. And we'll just run it for 2 iterations. And then we'll set the best answer equal to the value that's being returned here from this. And you can see the value that's being returned is the most visited child. So we'll take a look now, just running through this answer. So we start with iteration 1. The root answer is, I don't know the answer. And so we provide a first critique. Now there'll be 3 critiques because we're creating 3 child nodes. So here we have a critique. And then we're going to have an improved answer. So here's the first improved answer. And you can see it gets it right. It's an easy question. Then there'll be a second critique and a second improved answer. It's 1 because it's 0-based counting. And then a third critique and then a third improved answer. And then a random node is selected and a rating will be provided. So here we have a rating and we have the simulated reward. So yeah, the rating is given on a scale of 1 to 100. And then I just rescale it to be a float. So between 0 and 1. So it's 0.4. And yeah, you can see that this does highlight some of the shortcomings of using a language model to provide the rating. You can never guarantee that the answer is going to be entirely correct or the rating will be entirely correct. So then we move on to iteration 2. And this time we have an actual improved answer that we're working to improve. Here it is. It's, I'm not sure which node we're working on here, but there's some baseline answer that looks correct. There's a critique. Then there's going to be improved answer. Now this will be done 3 times. And finally, we're going to rate the answer and it's rating it here as 0.6. And I've only run 2 iterations. So the most visited child only has 1 visit. That's not very statistically significant and why you would want to run for many more iterations. And just last of all, we print out the best answer. So here the best answer gives the reasoning process and the final answer. So that was a trivial example for 2 iterations, but it just shows you the flow of how the process goes. And now for the moment of truth, let's see if Monte Carlo actually helps when we solve some maths problems. So I'm going to download the LightEval maths dataset. It's a question answer dataset. I'm just going to download 100 rows and we'll run on 1 row. For a baseline, I'm going to run with just a chain of thought prompt. So no Monte Carlo here, just to have a baseline on the question. And the question we have is, what is the 100th term of the arithmetic sequence here? 6, 10, 14, 18. And the correct answer to this is 402, by the way. So I'm querying the LLM, getting the answer, And the final answer the LLM projects is 398, but the ground truth answer is actually 402. So you can see the language model doesn't get it correct here in this case. So let's see if we can get a better answer if we use Monte Carlo. So we'll fetch a question and the answer. By the way, the answer here, it's not being fed in to the Monte Carlo process. It's purely for checking right at the very end. So all that we feed in is the question. And you can see that here, Monte Carlo tree simulation, we feed in the question, the seed answers. I've just got trivial seed answers like I don't know, and we'll run for 100 iterations. Then we'll print out the most visited answer, or the answer on the most visited child node, and then the actual ground truth. So I've run this for 100 simulations, and let's get to the bottom here. And you can see where the best answer is displayed just a little bit further. So the best answer after 37 visits, that's 37 out of 100. The best answer is 402, which matches the ground truth of 402 as well. So you can see by using Monte Carlo Tree Search, we are able to improve the answer in this case. Now, it's not a statistical guarantee that we have the best answer. The language model could be incorrect in how it evaluates this problem. And indeed, if you test it on different problems, it won't necessarily get them all right. But what it does do is increase the probability that you are going to get the right answer. Now, if the language model has absolutely no data that is relevant to the problem at hand, it's not necessarily going to give any improvement. It might just result in the same performance you would have gotten anyway. However, if varying the prompt typically leads to different quality answers, that is where Monte Carlo Tree Search can improve the performance. Now, I said I would mention a few limitations to Monte Carlo. First of all, correctness is not guaranteed if you're using a language model as a judge. In some cases, when you're solving, say, maths problems, you can run a Python program to check if the maths problem is correct. And then you can feed that back in, either to provide a rating or reward, or just to terminate the process if you've reached the correct answer. But if you're using a language model, it's only going to be probabilistic in what it says about the answer. And if it doesn't have knowledge on that domain, it's not going to be a good judge and not necessarily guide you towards the right answer or a better answer. The other thing you've probably realized is that Monte Carlo requires a lot of iterations, so it's slow and it's expensive. It's not the kind of process you would use if you want to have a chatbot that has low latency. It's more suited to refining maybe some reports if you want to improve on the quality of the reports, or if you want to improve on the quality of a more complicated analysis. So in short, Monte Carlo, best for high latency, not low latency, best for high latency, high quality tasks. And that's it for this demo of Monte Carlo Tree Search. Let me know if you have any questions below. The scripts are in the advanced inference repo. I'll put a link to the paper that this is very loosely based on. You can find some of the original code there as well in the GitHub, which I'll throw in the description below. Cheers.